Next speaker is Skylar Tibbits, director of the Self-Assembly Lab and also founder of several startups. Skylar's a research scientist at the MIT Department of Architecture. He's actually co-taught with Neil several times. He's a TED Senior Fellowship Award, lots of different things going on. I think that you'll find that Skylar's perspective has a very sharp eye on the applications that are coming out of some of this macro thinking that we've been presented with and some of these examples we've been presented with throughout the day. So, Skylar, the stage is yours.
So I have two main roles. The first role is the editor-in-chief of the 3D Printing Additive Manufacturing Journal. And I think that you'll see throughout the talk why this is quite relevant. But it's interesting, we've heard a bunch today on where 3D printing is going and some new technologies. And so I have to give a little bit of a plug for the journal that it's interesting because we're across many different disciplines and able to look at how technologies are developing and how it's expanding beyond just printing into all things additive. But the second one, which is what I'm going to talk about today, is I run a research lab called the Self-Assembly Lab. The Self-Assembly Lab actually grew out of architecture, which is where my background is. I was at MIT studying design computation, looking at how software radically changed the way we're able to design things. This is Sutherland's Sketchpad, one of the first, or the first CAD tool, which obviously has contemporary counterparts where we're able to design sophisticated things, simulate complex phenomenon. Design and software have become one, and we're able to design things we couldn't have designed without software. Everyone takes that for granted today. Every industry was radically changed, specifically design industries, because of computational power. Similar, Neil talked about how digital fabrication radically changed things. This is the first CNC machine at MIT, which has contemporary counterparts in CNC printing, CNC routing, water jets, 3D printing, laser cutting, et cetera. Computers connected with machines allow us to do things that we haven't done before. Everyone here is fairly familiar with all of that. Both software and digital fabrication are nothing new at this point. What my research lab focuses on is what happens after that. What happens after you can elegantly design something and you can have machines that produce those parts. Now you have all these parts that you have to assemble together through blood, sweat, and tears. So this manual process of assembly, we try to find ways that we can have more elegant scenarios for assembly where the materials have more information, where we can program these materials to change shape, change property, contain construction information, potentially assemble themselves, or collaborate with humans or machines to assemble better things. We specifically look at this large macro scale world, construction, manufacturing, product development, product distribution, shipping, this kind of messy human scale world, because we think there's a lot of opportunity to look at how we interact with materials. Instead of forcing materials together, trying to collaborate with materials, develop smarter materials so that we can eventually have smarter systems, manufacturing, and products. So we focus on three main agendas in the lab. The first one is, as the name suggests, we look at self-assembly. Self-assembly is where disordered parts can come together on their own without humans or machines. Mostly we see that at fairly small scale scenarios, and we try to demonstrate that at larger scales. This is probably the most clear example of it. It's a flask, you shake it hard, the components break apart, you shake it a little bit softer, and they come back together. This is a physical model of the polio virus. We did it with the molecular biologist Arthur Olson, who's from the Scripps right around the neighborhood. And so we demonstrated that physical components can produce these organized structures through a non-organized input from the user. So we're randomly shaking this thing, and it's not producing random results, but rather repetitive, precise results. There's no information in the user in the sense that I don't know what I'm building. I could be blindfolded and pick this up, or I could give it to anyone here and you could pick it up and still assemble the precise thing over and over and over again. So the blueprints in this case are in the components themselves, not in the user, not in the energy, for example. So then we study that in all sorts of scenarios, in big tanks of water, and fans, and tumblers, and shakers, and large-scale systems, and smaller scale. I'll show you one example of a larger scale scenario. These are 36-inch diameter weather balloons, so large modules, and they connect together to build large scale structures. I'll show a video and then talk to you about it. So this is roughly a 10 foot by 10 foot by 10 foot space frame structure that was assembled with helium-filled weather balloons. So the helium-filled weather balloons float around. We threw a party. People put energy into it. And you can assemble different types of structures. We're obviously in a closed environment there. But kind of the extreme scenario was that you could assemble things not on the ground, not with humans or big machines, but rather these large-scale structures could assemble, and when the helium dies, you're then left with this large space frame structure that would have been rather unwieldy or more difficult to assemble on the ground. The second category of research is what we call programmable materials. So the idea here is that you want to program materials to change shape, change property, change functional characteristic on the fly. And we specifically try to do this without electromechanical means. So without motors and sensors and robots and electronics, try to find ways to just fundamentally combine materials to have the behaviors of robots, but just materials themselves. And the way that we do that is we look at the materials and the geometry. The material properties are obviously the performance of the material. You might select metal or plastic depending on the application. The geometry is how you combine the micro and macro structure of that material, how you combine different material properties together. And by combining those two things, you can get different types of transformations when you activate it with the right type of energy. So for example, you might take metal for an application. Metal, you then think, okay, well, how can I activate that? You might use heat, for example. Or you'd go the other way around. My application has a lot of moisture, so you might want to choose a cellulose-based or a hydrogel-based material that's going to then react to that moisture. How can I design the micro-macro structure so that it folds to 45 degrees, for example? So you try to figure out these combinations in order to make actuators and sensors and all sorts of functional characteristics. The way that we started doing this in the beginning is something we called 4D printing. So 4D printing was a collaboration with Stratasys and Autodesk. It's now ongoing for a number of years. It was the simple idea that we wanted to take 3D printers and add the element of time. So add the fourth dimension of time, basically print things that could transform, reconfigure, change shape, change property. The way that we do that is we use multi-material printing. You print with different materials with different properties at the same time in different combinations and geometric configurations. The one that you're seeing most clearly here, the black material, is just a rigid polymer material, and that's essentially the geometry. That's the precision, the angles, the backbone, the structure. I think about it as sort of the braille. It's the geometric code for what it's going to transform into. And what's a little bit harder to see is there's a hydrogel printed here. It swells 150% when it meets moisture, and that gives it the amount of energy to transform from one shape to another shape. So we've done all sorts of different combinations of these materials to go from any one shape to any other, to go from 1D to 2D, 2D to 3D, 1D to 3D, for example. So you'll see here a single strand that's printed and it self-transforms into a cube, a strand that self-transforms into MIT, a surface into a truncated octahedron, surface using curved crease origami with Eric and Marty Domain to make saddle structures, local expansion and contraction to make doubly curved surfaces from flat sheets, even 50-foot long strands that transform in swimming pools, much like very large proteins, for example. So we've tried to make many, many combinations of these that can go from one shape to another shape, all with multi-material printing, without assembly, without motors, without extra devices and sensors, et cetera, all just transforming based on moisture. But we kept getting this same question. Lots of people would come and say, this is super interesting. How can we use it for planes or shoes or cars or medical devices? How can we program other materials? How can we use other industrial processes? And so since then, we've tried to develop a way to program many, many materials. And so that's why we're calling these much larger category programmable materials. And this is an ongoing collaboration with a lot of people, from materials developers and suppliers, software companies, product designers, mathematicians, computer scientists. We've developed a number of different materials. I'll show you 3 examples. One is a printed wood. So literally, we're printing wood. It's essentially an MDF. It's sawdust and a polymer. You combine it, you print the grain, and by printing the grain, you get the wood to swell based on moisture. So the grain pattern then dictates the type of transformation. Second material is textiles. So there's 2 ways to do it. You can print on top of the textiles after you've pre-stretched it. By pre-stretching it, you give it that activation energy. You print a pattern. After you print that pattern, it then can self-transform into different shapes for like pleating and tufting. We made a shoe that can self-transform. You can also do active polymer. So this is a thermally responsive polymer. So you can combine that with any textiles or leathers to make smart clothing, et cetera. The third one is composite, so carbon fiber, Kevlar, fiberglass. You can print active polymers on top of that, and you can make carbon fiber that self-transforms, folds, curls, twists, et cetera. This is a light active carbon fiber for active shading. We've worked with Neil's lab and with Airbus on a component for their jet engine that can open and close to control airflow to the engine. So there's a lot of aerodynamics applications, car applications, furniture, clothing, medical devices, et cetera. More recently, we've started to look at this textile scenario, but trying to scale up. What are the properties of weaving specifically that allow structures like a Chinese finger trap to transform from a single cylinder to variable diameters? It can taper, it can bend, it can curl and twist. There's really interesting properties in weaving specifically, and we're interested in this in large-scale scenarios. So just as we were showing textiles that don't need actuators or motors or sensors for clothing, can we do the same thing for bridges, buildings, canopies, stadium roofs? Instead of having big electromechanical structures, can we have basically large-scale woven structures? This is a tower that we recently built at MIT. It's a 65-foot tower that's a fully woven structure, trying to show that we could have architectural textiles that you can transform. So this is essentially a woven piece. It's with a crane. You lift up all of the rods, and then you go around in a dance, and you can weave this large structure, so it's a large textile. After it's woven, you can then make it do all sorts of things. This is a 20-foot example that we did in our courtyard. So this is where we were load testing it and measuring all the behavior of it. And this is the final 65-foot one done with Tate Towers. So there's a small person at the bottom here. It's essentially a large puppet that, with very small changes at the base diameter, you can get very large transformations across it, and you can make it do all sorts of different structures. A more specific example of this we recently did for a pop-up meeting space. So basically, think about meeting spaces, phone booths, conference rooms, et cetera. You can make spaces that open and close, expand, contract. In this case, the diameters are fixed, but the height is transforming. The next one that we're looking to do is that you can vary the diameter of these, so you can transform for a few people or many people. So we think there's all sorts of applications in woven type structures at large scales. So we're really working on smaller scale things for printing, for example, in polymers, to textiles, composites, larger scale woven structures, et cetera. The last category of research that I'll talk about briefly is essentially phase change. So instead of assembly, the first work, instead of shape change, the second work, this is about phase change, things going from solid to liquid, liquid to solid, stiff to flexible. And one of the ways that we do that is through granular jamming. So granular jamming, everyone here is probably familiar with. When you go to the grocery store and you buy coffee, it comes in a vacuum packed seal, and it's rigid like a brick. Or when you're at the beach and you jump or you hit the ground, it's really hard. The sand is really rough, but if you sculpt it, it's really soft. So this is granular jamming, where the particles jam and they become stuck. And so we've been developing all sorts of different applications of this. One that I think is specifically interesting and relevant to the printing conversation is a collaboration with Gramazio Kohler Research, where we were rock printing. So basically, we take a bunch of rocks in a container, and then we spit out a fiber, literally a string. And that string and that rock, loose string, loose rock, allow it to granular jam. So we've done a project at the Chicago Architecture Biennale. We built a 4-meter tall tower. So basically, we have a big bed. This is that yellow bed. It's rock, string, rock, string, rock, string, over and over and over again. And when you move that bounding box, all of the rocks that didn't have the string fall away. And only the rocks that did have the string jam. So this is a loose rocks, loose string, no adhesives or anything. It's completely jammed, and we put 3 tons on top of this. So it's a load-bearing structure. It's essentially going after reversible concrete. So you want to be able to pour a structure like concrete. You want it to be able to instantly cure, no cure time, and you want to be able to reverse it. You want to remove it, reuse it, no waste, full recyclability of the materials. So this is a quick video that I'll probably scrub through here, but it shows the disassembly of it. So essentially, we wind up the string. So you have this 4-meter tall structure, and you pull the string out, and it disintegrates. So eventually it turns into a big pile of rocks. Wait, let's see. Yeah. So more recently, we've done a version of this where we built a wall. Let's see, maybe I'm stuck. Yeah, we've built a wall, 10-foot wall. We're trying to go faster and faster with this, and that essentially means lower and lower tech, meaning you don't want a robot to spend a week building a 4-meter tall tower, but rather we want to be able to go super fast, super quick, super low tech to be able to spit this out like concrete and have reversible walls. This is a 10-foot wall that we did in a few days, in a few hours over the course of a day. And that wall is load-bearing like the previous ones. So where are we going with all of this? To me, this image is the epitome of today's manufacturing construction. You have lots of trades, lots of components, lots of energy, either skilled labor, or the holy grail is that robots are going to save us in manufacturing, and they're just going to get cheaper and cheaper and more precise. But we're trying to find an alternative solution to that, and we really think it lies in materials. That it's not about smarter and smarter or cheaper and cheaper robots, that it's materials can now become robots, that we can have robots without robots. We can have robots that are sensors, robots that are actuators, robots that have logic and simple things like that, and they're all materials. So the materials can be sensors, actuators, and logic. So as Neil was talking about, today we're programming computers and machines, and what we think is that tomorrow we're going to be programming matter itself. Thanks so much.